So what I will do now is just, I will kind of, because when we did this, started with simple harmonic motion. So the topic is not simple harmonic motion. Simple harmonic motion is the beginning of topic C, which is waves. So we've done A, except for relativity, and we will now do C, which is waves. And the beginning of waves is simple harmonic motion. So very important. Today we will cover the standard level part. Tomorrow it will be HL only. But for those who enjoy coming in 8 o'clock in the morning, what I'm going to do tomorrow is basically math. So the math I'm going to do tomorrow is AA math for standard level. So you can not show up for tomorrow, but eventually you have to learn it. So those who want to spend some time on learning the math concept of trigonometric functions, they can do that as well. But I'm not going to force you. You can also learn that in math, and I will probably cover that also. But what I'm going to do today is I'm going to do some revision of simple harmonic motion and just talk about what is simple harmonic motion and talk about energy in simple harmonic motion. So SHM, that's just short for simple harmonic motion. And what you will or have to know that in order for have simple harmonic motion, for an object to undergo simple harmonic motion, which is a back and forth motion, you will have to have an acceleration that is proportional to the displacement but opposite directed. So mathematically we have a condition for simple harmonic motion, which is acceleration is equal to minus omega squared times x, where x is the displacement. So what this equation tells us is that acceleration is proportional to the displacement So to have simple harmonic motion, the acceleration of the object has to be proportional to the displacement away from the equilibrium. So displacement is displacement from equilibrium. Acceleration is opposite directed to the displacement. So that is basically what the condition for simple harmonic motion is. And acceleration is proportional to the displacement. This is the acceleration and x is the displacement. And the minus sign is the one that guarantees that the acceleration is opposite directed to the displacement. Yeah.
I was just wondering if that is x or if you're multiplying.
No, that's just if I wrote multiplication sign, then it would be two sums. So that is that was x.
Alright.
And in green, I can write what is omega. What do we call omega? Omega is either called angular velocity. Here we use omega is angular frequency. So, but this is much easier to understand if we kind of look at an example. So one of the easiest theoretical example is what we call here mass spring system. So you have a spring attached to the wall and attached to a block, which can slide frictionlessly on a horizontal surface. Not that easy to do in practice, but theoretically, the simplest example of simple harmonic motion. So we have here a spring and the block lies at rest. So here the spring is not extended, and so the block lies at rest at the equilibrium position, which I call x equal to 0. So when I talk about x is equal to 0, that is the equilibrium position. Then I pull on the block. So I extend the spring. And that means that I will have a force on the block by the spring trying to pull it back. So that force from the spring onto the block, that's what we call the restoring force. So if I pull the block to the right, I have a force to the left. So the force is opposite directed to the displacement from the equilibrium. So I draw here a force F. So what's going to happen to the block if I release it? If I pull it and release it? Yeah, you sure? When we did the full math in HL. It doesn't make sense to talk about angles here. There's no angle here. What is angular velocity? What's angular frequency? That's just what we call it. They come from the math. I cannot explain where the angle is here. That's just a constant, proportionality constant. Yeah.
Is it something with the sine waves and stuff?
Yeah, it has everything to do with the sine waves and the mathematical description of a sine function. Yeah. Yeah.
My question is that when you got from acceleration to angular acceleration,
Yeah.
what is the formula? Like, how did you?
Well, yeah. So basically, I just look at this expression and compare it to this one.
Okay.
So basically, I just see that, okay, here I have acceleration, a constant times x. Here I have acceleration, constant times x. So I just identify that this is equal to this. Yeah. Yeah.
Isn't the box sliding, so is there no friction, or is that frictionless surface?
Yeah, there's no frictionless surface, yeah. If I included friction here,
Then you'd have to include it with the force, it would be force.
Yeah. Yeah, and then it wouldn't be simple harmonic motion anymore. Yeah. All right. So why is this useful in physics world to find the angular frequency? That is because, do anyone remember what did I use the omega for? I used it to find something that is quite relevant. Time. The period. The time it takes for it to go from one to the right, to go to the left, and back. One complete oscillation. The time of that is the period. So the period, that is t is equal to 2 pi over the angular frequency. So in this case, you would take this expression 2 pi divided by that expression to find the period. So if you get a system like this and asked to find the period, that is on the data booklet, maybe this one is on the data booklet. Simple harmonic, simple pendulum, the formula for period is in the data booklet. But on the exam, they can come up with an entirely new scenario where an object is undergoing simple harmonic motion. To find the period is actually a quite complex job on evaluating the forces, finding an expression for the angular acceleration, of finding the expression for the acceleration, comparing it to the condition for simple harmonic motion, and then to apply that formula here. That is somehow, it's simple to ask the question, not always as simple as solving the question. Sometimes you can ask a quick question which requires quite some time to solve. That is what we like for a physics teacher. Limited writing on our behalf, a lot of work on your behalf. I want to say I'm kidding, but we all know that's not true. But I want to talk a little bit. So before Christmas, I gave you a problem sheet where I gave you multiple scenarios where you will find the period. I assume that you did it over the Christmas. But I now want to talk a little bit about what simple harmonic motion actually looks like, because it has everything. It's a very mathematical topic, really. So when we have an object where the acceleration is proportional to the displacement away from the equilibrium, and the acceleration is opposite directed to the displacement, the motion is going to look like what we call a sine function or a cosine function. It will kind of move back and forth along like this. If it starts at equilibrium, move to one extreme, back to equilibrium, then to the other extreme, and back to equilibrium again. And it will kind of continue to move like this. Back and forth, with no loss of energy. If you have energy loss, the amplitude of this will change. It will start to move like this and that, and it comes move less and less to the right and left. And if the acceleration is proportional to the displacement, the period is independent of the amplitude. By that I mean, if I pull it 2 centimeters to the right and let go of it, it will have the same period as if I pull it 4 centimeters to the right and let go of it. So the period does not affect it by how much I'm moving it to the side. amplitude is independent of the amplitude. That's only true if you meet the condition for simple harmonic motion. So for a simple pendulum, here's my keys again. If I pull it like this and let go of it, I can measure the period. If I take it a little bit further and let go of it, the period will be the same. But if you remember the lesson I had, that the simple pendulum only meets the condition for simple harmonic motion for small angles. Because when I did derive the equation for simple pendulum, I used a small angle approximation. So the simple pendulum is only a simple harmonic motion for small angles. For greater angle, it will not be a simple harmonic motion. And not being a simple harmonic motion, you can get a curve that looks something like this, but the period will not be independent of the amplitude. Yeah.
So, for it to not decrease, does that mean that the forces are balanced and there is nothing acting against it?
Yeah, I will say that the force, that there's no forces that gives you any energy loss in the system. So if I have a pendulum moving back and forth, if there's no friction, if there's no air resistance, it will just keep moving back and forth with constant amplitude forever. What makes it get smaller and smaller amplitude is due to air resistance and friction. Yeah.
So you said that the simple pendulum eventually doesn't become simple harmonic motion when the angle is too big.
Yeah.
So then what examples is there for a situation where it would always be true?
Yeah, so that the question is that when is a simple pendulum a simple harmonic motion? Is when the angle is less than 10 degrees.
No, but other examples for simple harmonic motion.
Yeah, for instance, this one. This is simple harmonic motion.
And that's always going to be true.
Unless we get friction.
Okay. Yeah.
If I include friction here, if I just start to say here, I want to have friction in this case. Friction is independent of the displacement. So that means that by including friction, that will mean that the acceleration will no longer be proportional to the displacement.
Okay. And then for the simple pendulum, are we required to find out when it stops being simple harmonic motion?
Yeah. Because I think you have to know how to derive that equation.
Okay.
Yeah. And by deriving it, you will have to use the small angle approximation.
Okay.
And you have to know when to do that. Yeah, yeah. So tomorrow we will talk a lot about that function. But this is how kind of a simple harmonic motion looks like. Displacement from equilibrium and time. Just moves back and forth and can be described like a sine function, like this. And the last thing I want to talk a little bit about is energy. And for standard level, we're not going to do it too mathematically. We're just going to do it more in terms of word, but some equations. But if I take this object here, I take this block and I pull it to the right and I let go of it. It starts to move, right? You agree on that? You're going to picture the situation. I pull it to the right, I let go of it, it will start moving. and moving is having a velocity. So when an object has velocity, it has one specific type of energy. What type of energy is that? Kinetic energy. So when this block is moving, it has kinetic energy. But if I hold it here, in this position here, and I let go of it, and it gets kinetic energy. That means it has to have some other type of energy. Potential energy. So by holding this object here, I get a form of potential energy. What gives me this potential energy? What is the object? Why does it have potential energy? What gives it this potential energy? Yeah, there's no velocity, it's only potential energy. But why does it, what is making this object move?
Isn't it the spring?
Yeah, the spring. So, the energy in simple harmonic motion is one we have to talk about kinetic energy, which is given by one half times m times v squared. That's the kinetic energy. And sometimes we have potential energy, or what we call gravitational potential energy. So now I just say here, I just call that, right, grav for gravitational potential energy. That is given by mgh. But here, I don't have any gravitational potential energy. There's no change in height here. There's no gravitational potential energy. But it's another form of potential energy.
It's 1/2 of kx.
Yeah. It's given by a formula. It's a potential energy due to the spring. It's called elastic potential energy. And that is given by, and it can be derived, but it's basically just 1/2 times k times x squared. So here in this case, we have two types of energy. It's kinetic energy and it's elastic potential energy. When I pull this block to the right, I'm extending the spring, so there will be a potential energy stored in the system. Now let go of it, that potential energy will be transferred to kinetic energy. And if I have no friction or air resistance, the total energy in the system, so I can now write what I before called mechanical energy. I write T here for total energy. I write that is the sum of kinetic energy plus the potential energy. And I just write here P for potential energy. That can be gravitational or elastic or both, depending on the system. So the total energy is the sum of kinetic energy and the potential energy. And the potential energy can either be elastic or gravitational.
So it's not like mechanical energy?
Yeah, it is mechanical energy. But so now the book decided on they want to have a T there instead of just an E there.
So total.
Yeah, so but it basically is what we called the total energy before. Yeah.
Why do we not account for recoil
Hmm?
in this? Why do we not account for recoil in this?
The recoil wouldn't affect. Yeah, the recoil here. Yeah, you would, but you would assume that you have attached a spring to a wall.
Yeah, but don't you still have recoil from the spring if it's moving?
Yeah, but the recoil won't have an effect if the wall is fixed. It would be very complicated if we allow the wall to move.
if you have a spring pendulum, is it possible for it to be simple harmonic motion? So if it's a pendulum on the spring. So
Yeah, I don't quite have that answer right in the top of my head. No,
is there something you're kind of reading? Could it theoretically be simple harmonic motion?
I don't think so. No, I know it wouldn't. No, it wouldn't.
Because then
Pull it down.
So if I take it will be if I do it up and down, it will be
Yeah.
simple harmonic motion. If it's like this, it will be simple harmonic motion. But I don't think the combination of it will become simple harmonic motion. I'm not entirely sure. But what is very important here to realize when dealing with simple harmonic motion is that the total energy is conserved. So there are no energy loss. Here, I will only have potential energy. Then I will start to move towards equilibrium. At equilibrium, there's no potential energy, only kinetic. It will then move to the left, back to only potential. But the total energy is conserved in simple harmonic motion. Yeah.
Is there a reason why in the example, in the second photo, the force is coming from outside of the box, but then when the spring is like closed, it's coming from there?
No, it's always acting from the point of contact.
Okay.
Point of contact with the spring and the box. Yeah.
Okay, thank you.
So I think that summarizes. So today you're gonna work with problems involving energy. I want to say that if you want to measure the period, here the time is 0. A full oscillation from a graph here. This time from here to here, that is 1 period. Or here to here, that's 1 period. Or from here to here, you have 1 period. So now I'm going to give you a problem sheet where it connects simple harmonic motion to other parts of physics that you have been working on. So remember that these practice problems, they are a part of the syllabus. So